speaker, Professor Donna Testerman from the École Polytechnique Fédérale de Lausanne. So she's working in representation theory and subgroup structure of an algebraic group. About that. And of course, it's entitled Representation Theory of Algebraic Groups, Methods and Applications.
Thanks. Okay, so I have to, my aim is to get to talking about the representation theory, but I have to put in place a little bit more of structure theory of reductive groups, building on what Meinhof talked about this morning. And so the first maybe 20 minutes of today's talk will be not about representation theory. Okay, so I'll start by recalling two of the objects that Meinhof mentioned. So I take G to be a reductive linear algebraic group over a field K. And then we had a Borel subgroup and a maximal torus. So fix a Borel subgroup B and a maximal torus contained in it, maximal torus, T contained in B. All right, so I want to introduce sort of a set of combinatorial data that's linked to this picture here. So set X of T to be the character group of the torus. So that's the algebraic homomorphisms, so algebraic group homomorphisms, I won't write this anymore, from T into the multiplicative group of the field. And Y of T to be the homomorphisms that go the other way. So that's the homomorphisms, again, algebraic, from the multiplicative group of the field into the torus. All right, then there's a natural pairing between these two. So I don't know where I want to write here. Write somewhere. Maybe I won't use all the boards. Then there's a natural pairing between X and Y into the integers, given by, so I take a character and something I'll call a co-character, and I map that to an integer m, and this integer m is given by the fact that if I do lambda composed with mu, then let's see, mu goes from the field, right? So that's a map from the field into the field. It's an algebraic map of a morphism of algebraic groups, and maps like that are given by an integer power. And so lambda composed with mu of t is equal to t to the m. Okay. All right. So that's the definition of this pairing. All right. It's a perfect pairing in the sense that all the homomorphisms from X of t into the integers is given by finding a mu. Okay. And all the homomorphisms from Y of t into the integers is given by finding a lambda. Okay. I won't write that down, but it's got some nice properties, this pairing. Okay, so now there's a certain subset of the character group and a subset of the co-character group that will play an important role. So we define a certain subset of X of t and then also of Y of t. Okay, so I'll say that alpha in X of t is a root. Right? If there exists an injective morphism of algebraic groups, if there exists an injective morphism mu alpha of algebraic groups that goes this time from the additive group of the field, okay, into the group G, such that the image of it, the image of this, well, it's going to be, so what is it going to be? It's going to be some closed one-dimensional unipotent subgroup. And I want it to be invariant, so normalized by t, so that this thing here is a closed, well, necessarily closed, connected, one-dimensional unipotent subgroup. All of that we get by unipotent subgroup, but normalized by t. normalized by t. Okay, not just that, I haven't said anything about alpha. So normalized by t in such a way that the action of t on that group is given by this character alpha by t. And for all t in t, when I take t mu alpha and for all x in the field, when I take t mu alpha x t inverse, this is mu alpha alpha of t x. Okay? So this function, this character, tells you how the torus normalizes that one-dimensional group. Okay? So if you find such a one-dimensional group, then you call this character a root. Okay? That's not the only way to do it. I mean, if you've already learned this, then you would be expecting me to talk about the Lie algebra, but this is another way of finding the roots. Okay. Set U alpha to be precisely this one-dimensional group mu alpha of x in the field. Okay, so that's what I call a root group, the root group associated to alpha. Okay. Okay, and set R to be the set of roots. Set R to be the set of characters that have that special property, alpha as a root. Okay? All right, so the amazing thing is that there's a list of properties now satisfied by this, this set of characters. I mean, a priori, it's just a set of characters, all right? So then one can show, then, okay, so this is a then with a lot of work to do. But anyway, let me tell you some things that are true. That if alpha is a root, then minus alpha is also a root. Okay, so that's one thing. A second thing is that there's a map from SL2 into G. There exists a morphism. Phi alpha from SL2, okay, into G, such that this root group that we found is just the image of the upper triangular matrices, and the negative root group is the image of the lower triangular matrices. So phi alpha of this is equal to mu alpha of x, and phi minus alpha, because I know it exists, of this matrix is equal to mu minus alpha of x. Okay, so for each root, I not only get a root group, and I get this other root group that goes with it, but together, that's some group that's an image of an SL2. Okay, so that's nice. Oops, I can't do that. That was a mistake. All right. All right. All right, so for each root, I have two root groups. And when I look at them, the group that they generate, that's an image of an SL2. 3, let's see, am I numbering this? 1, 2, 3. For alpha, a root, there's, I'm going to define a coroot. So define alpha check, which is going to be a coroot. Okay, so that should be a way of mapping the field into the torus, right? By alpha check of C is equal to this phi alpha over there of this matrix here, C inverse. Okay, for all C in K star. Okay, all right. Okay, so I've defined it. Then there exists an S alpha dot, I think. I'm going to get this notation right. An S alpha dot in the normalizer of the torus, okay, such that this S alpha dot lies in the image of this SL2. So the S alpha dot is in the image of phi alpha, okay. And if you set S alpha to be the element of the Weyl group that goes with that S alpha dot, then can say something about what element of that element of the Weyl group is doing. Then setting oops, S alpha dot. Then setting, well, S alpha to be S alpha dot T in the Weyl group. All right. We have that S alpha chi, for all chi, where am I taking chi? Chi in x of t. S alpha applied to chi is just chi minus this perfect pairing, right? Chi with alpha check alpha. Okay, for all chi x of t. Okay, so somehow this alpha check is a special co-root that's linked with my root alpha. Okay, and now Meinhof didn't talk about it, but S alpha is something that is in the Weyl group, so it's in the normalizer of the torus, and naturally acts on this character group. Okay, so I mean you can write that down, so that's not hard to see. And now I'm telling you that the action of this particular element of the Weyl group, when it acts on the character group, it does this. Okay, all right. Okay, so a few more ingredients. Yes.
So using the phi alpha, can you take
yeah, exactly. So you really, yes. So you can really think of it as being the Weyl group element here. Yeah. Okay, so now I'm going to, okay, so then moreover, the Weyl group is actually generated by these S alpha dots, alpha and R. Okay, so I've got enough of them, right? Okay, so now, okay, R. So I'm going to view R now. Viewing R, I guess that was number 3. All of that was about the Weyl group. So this is number 4. Although for some reason I didn't. Where did I write that down? Oh yeah, I wrote it at the bottom of the page. Okay. So viewing R as a subset of some Euclidean space that I'll define like this. Viewing R as a subset, okay, of x of t, tensored over Z. With R, okay? Then it turns out that R, okay, so this is some Euclidean space, E, right? It turns out this R is actually a root system inside of this Euclidean space in the abstract sense of root systems, okay? Miracle, I mean, really. So we start with a reductive group, all right? And it's a group. It's got the structure of a group, right? It's a variety. Okay. And then somehow, almost like out of the air, right, we find a set of certain characters, right, on the maximal torus that we fixed. And then we find that these characters have some nice properties, okay? And then we have this natural Euclidean space here, and this is going to be a root system in there. So viewing R as a subset of this, R is a root system in the abstract sense. A root system in, does somebody want to, if I don't write something else, this is not a correct statement. Well, you know, if you've got, I mean, you can put 1 on it, okay, so that somehow it's consistent with what you've set up over here. That's not the mistake. Yes?
It might not span.
It might not span. Excellent. Okay, so it's not a root system here, because somehow this thing might be too big, okay? So it's a root system in the part, well, where it should be. Okay. And maybe that's what I want to call E, but anyway, it does not, I think I'm not using E. So it's a root system there. Okay, thank you. All right, because, okay, well, I'll say something in a minute about that. But somehow, I might not have enough things to really span this whole space, but I can certainly span that one because I set it up that way. All right. Now, I've got one root system. I've also got another one. Right, so I can say, let me say one more thing. If the group is not just reductive, but semi-simple, then this thing does span E. Okay, so then we're okay. Then I don't need to make this remark. So if G is semi-simple, that's a parenthetical remark. If G is semi-simple, so remember, mine also talked about if you've got a reductive group, then it's a product of its derived subgroup, which is a semi-simple group, and this central torus, all right? So if you don't have this central torus, okay, then if G is semi-simple, then this is actually equal to E, okay? So then you don't have to, okay, then you really have a root system in that place. Okay, so that was number 4. Number 5. I'm building up this list of data. Okay, set R check to be the set of alpha checks, where alpha is a root. Okay, then this is also a root system somewhere. And where could it be a root system? It will be a root system in the analogous object like that, where I put a y there. Okay, so then R check is a root system in, well, R check R viewed as a subset of that space. Okay, some analogous object. Okay, and one more thing to link all of this back to B. So all of this, so all of this really is coming to us from the torus that we fixed at the beginning, right? Yeah. And we haven't talked about, I haven't linked it at all to the choice of Borel subgroup that I made at the beginning, okay? And so finally, there's a base or of this root system, or a positive system in this root system, such that the Borel is generated by the positive roots in the torus. So there exists a base of R, or a positive system, doesn't matter, such that the unipotent radical of the Borel subgroup is generated by the U alpha, where alpha, there exists a base delta of R, such that the unipotent radical is generated by the U alpha, alpha in the base, or, I mean, if you like, alpha in the positive system that corresponds to the base. Okay, same difference, all right? So then your Borel subgroup looks like the semi-direct product of this torus that you fixed at the beginning and the positive set of roots, a certain positive set of roots. All right, okay, so we start with a reductive group, and we fix a torus and a Borel. We get a set of roots. These roots, we call them roots because they actually are a root system somewhere. We get a set of co-roots. Right. So if you know Lie theory, and you know the classification of the semi-simple Lie algebras, then somehow we stop there, right? Because if you have a semi-simple Lie algebra, there's a root system that goes with it. And if and only, right, bijection, okay? But now, if you're wanting to understand reductive groups, or even semi-simple groups, you've got to go a step further, because just the root system is not enough. Okay, so we need these two root systems and the thing that links them. You know, somehow there's this pairing between the alpha and the alpha check. And so we need all of that in order to be able to state a theorem that says there is a combinatorial object that classifies reductive groups. Okay, so let me, now I'm not going to actually define, I'm poorly using this board. Okay, so I'm going to bring this down so the next time I remember. Okay, so I'm going to not really define the next thing I say, but at least I've put in place kind of all the ingredients and then state a theorem. Okay, so there exists a notion of a root datum, which is more complicated than a root system, but anyway, so root datum, and I'm not going to define it. But what the root datum should be is sort of like this: X, Y, R, and R check, okay, a quadruple. And the X and Y should be free abelian groups of the same rank, X and Y free abelian of equal rank. Okay. R inside of, well, okay, so once it's free abelian, then I can tensor over Z with R. Okay, so I won't write all that. Okay, I will write it, but anyway. Okay, then R should be a root system in there. Okay, a root system. Okay, so it's the same problem as before, is that it's not actually a root system in there. You have to view this as a Euclidean space, and then it's a root system in the space generated. Okay, a root system in that. Okay, the Y should be a root system in the R check. Okay, the R check should be a root system in Y. Okay, so I'm not going to write down all the details because we already said that before. And there should be a bijection between R and R check that satisfies some nice properties. Okay, and that I'm not going to write out. And a bijection between R and R check, alpha goes to alpha check, that satisfies some things. Okay, and I'm not going to write all that down. But anyway, look at free abelian groups of the same rank, a root system in something, and some bijection that has to satisfy also some sort of combinatorial looking properties. Okay, so Chevrolet classification theorem says that two things. If you give yourself a root datum, there is somewhere out there a connected reductive group such that its set of objects x of t, y of t, r check is a root datum, is that root datum. And if you give yourself two distinct root datum, so there's a notion of isomorphism of root data. If you give yourself two different ones, then the groups that you are associated are not isomorphic. Okay, so it's a classification theorem. So the Chevrolet classification theorem. Let G be connected reductive. Then, with the notation that I set up above, then this x of t, y of t, r check is a root datum. Okay, I didn't quite define it, but is a root datum. Okay, so that's the first thing. G is determined up to isomorphism by that. So there is a notion of isomorphism of root data. Okay, G is determined up to isomorphism by its datum, by its root datum. Okay, and for any root datum, there is a connected reductive group realizing that. Okay, for any root datum, there exists a connected reductive group. Okay, that realizes it. All right. You might wonder then, how does the root system recognize whether your group is semi-simple or not, or simple, say? And so the root system recognizes that, because if the root system, if G is semi-simple, then this thing should generate really the whole Euclidean space we were looking at, and if G is simple, then the root system should be indecomposable. So that's like the Lie algebra theorem. Okay, so that part's the same. So the real complication is precisely, okay, so why is there a complication? We see immediately with an example why there's a complication, right? Well, SL2 is a really nice linear algebraic group, and so is PGL2, okay? And they have exactly the same root system, okay? So it's only this pairing between, X and Y and R check and all that, okay? It's only all of that that distinguishes SL2 and PGL2. All right? So it's clear that the root system isn't enough. But what's amazing is that this is enough. All right? So it's a really wonderful theorem. Why doesn't the pairing come into?
Is it included in the data?
Yeah, it has to be included. So there's properties. So I didn't say there's this bijection, and then there are some properties that have to be satisfied. So it definitely is part of the story. Definitely. Yeah. And I didn't want to write it all down. Yeah, sorry. Okay. All right, so that took a little bit more time than I wanted it to, but anyway, I hope that helps. So now we have a classification theorem. And so now I can talk about roots whenever I want to. I can talk about the character group. All of those things will, and the Weyl group, as Mine already defined it. And all of those things will play a role in the representation theory. Okay. Okay, so now, new chapter, representation theory. All right. Okay, so I'm going to start with just any old linear algebraic group defined over my fixed field. And we want to consider representations that live in the world we're talking about. So we want maps from G to GLV, say, that are maps of linear algebraic groups. Okay, so that's the first thing. All right. So I think I don't have to write all this down here because Mine said that. So let G be a linear algebraic group. Then a linear representation rho of G and K, so some finite dimensional representation, is said to be a rational representation if it's a morphism of varieties, right? Is rational if rho is a morphism of varieties. All right? So what precisely does that mean? It's not complicated, okay? It means that somehow, as Meinhof was saying, the map should be given by polynomials in the coordinates. And so precisely, let me say something because I'm going to want this notation later. So when you have a linear algebraic group, well, it's an affine variety, and so I say K of G is the K algebra associated, or the coordinate algebra of G. You know, so G is some closed subset of an affine space, and then you take the ideal, it's the zero set of some ideal of polynomials, and then you can take your whole polynomial ring and quotient out by that ideal. Anyway, you get functions on the group, okay? And so saying that you have a rational representation or saying that this is a morphism is the same as saying that the map, so this rho, is rational if and only if the map G, so I take an element of G, goes to rho of G ij, lies in K of G for all ij. Okay? So the coordinates that you see in your matrix, okay, so taking a G and then mapping it over to some coordinate, should be one of your nice functions in the group. Okay? All right. Okay, so now for the representation theory, so that's what I said, a linear representation, so that means I have n here, okay? So for the representation theory, actually, sometimes it's necessary. I don't build representation theory, I consume it. But for the people who build it, then I mean, it's absolutely necessary to study certain infinite dimensional representations. So let me tell you what I mean by a rational representation when it's infinite, okay? Or a rational module. So a G module, well, definition. A G module V, so now V could be infinite dimensional, is rational, okay, if, well, first, every time you take G and a vector, so take a V for all V and V, so every time you take a vector and you act with G and you make yourself a subspace, okay, that should be a finite dimensional space, okay, so the dimension of this is finite, okay? So let your group act. It's a module, so let it act. That should be finite dimensional. And for every finite dimensional G submodule of this thing, that should give you a rational representation in the sense of that, okay? So every finite dimensional G submodule of V affords a rational representation in the sense that I already defined, okay? Okay, So somehow you can cover up your space. Every vector lies in some G invariant finite dimensional subspace, and all of those have this property here. Okay? Okay, so now let's see some examples. Yes?
Is this going to be enough to do Fourier analysis on G? Some of us actually use the representations to do stuff.
What do you mean by is this going to be enough?
You just allowed infinite dimensional representations in the door. Is that class and your class enough so that I have a Plancherel theorem or Fourier inversion theorem? Or,
I don't know.
Okay. Thank you.
Does someone in the room want to does someone in the room want to answer that question? Bob.
Usually there's a bifurcation that happens between the algebraic theory and the unitary theory. And we don't care too much about the unitary theory this week. Okay. So I mean it's a different story.
Those are two answers. Thank you.
Okay.
I take it back.
It's okay. It's okay. Examples. Let's see. Let's take, okay, the easiest ones at the beginning. So let's take G to be G is GL E, where E is KN. Okay, so I just take the mother of all of our algebraic groups. So then G acts naturally on a bunch of spaces associated with E. So you could take the E-fold tensor product. You could take the I-fold tensor product of E, the ith exterior power, the ith symmetric power. You know, all very natural representations that are associated with the group GL, and those are all rational. Okay, it's pretty clear they're all rational. You know, you start with something that the coordinates are really the coordinates in the matrix group, and then you do something to those. That's a very polynomial behavior. Okay, so those are all rational representations. And in fact, since our G, an arbitrary G, is going to be a closed subgroup of this, right? So I could just precede this by some H that is itself a linear algebraic group as a closed subgroup of G. This E and all of these other things I wrote down here will also be rational representations for that closed subgroup. Okay? So that's already a big collection of some very natural representations. All right? So I won't write that one down. So that was my example 2, but I won't write it. Okay, so let's look at an infinite dimensional one, because I said we maybe care about those. So this K of G, so this coordinate ring that's associated with our group is some big K algebra. Okay, so my numbers are going to be off. So now I'm at 2 instead of 3. 2. Okay, so G acts naturally. Well, naturally, I'm going to tell you how. Actually, it acts naturally in a couple ways, so I'm going to give you one. Naturally on the coordinate algebra. So for X in G, then I'm going to define an operator lambda X, which is going to be a linear map K of G. And so lambda X should take a function on G, right? So it takes a function on G, and it should give me back a function on G. And so that should be f of X inverse G. Okay, so it's some kind of left multiplication, but the inverse is there, so it is an action. Okay, so then, so a good exercise that I'm not going to do, but I wrote it down in my notes, it's a nice exercise, is to convince yourself that that makes this thing into a rational G module. Okay, so remember, a rational G module, I mean, what you have to check is that every vector, lies in some finite dimensional subspace, and that's nice. That's a good exercise. So this K of G is a rational G module. Okay, so that's one. Okay, another one, important one. All right. So G also, so this was some kind of this was some action associated with left multiplication, and now I'm going to do an action, define something associated with the conjugation action. Okay, so for x and g, let's let I sub x be the conjugation associated to x. So for x and g, let ix be the map from g to g, which is conjugation. Okay. And then, okay, whenever you have a map from G to G, you get an associated map on the K algebra. So then Ix star goes from the K algebra to the K algebra. Okay. So you proceed by your I map. Okay. All right, so that turns K of G also into a rational module. So K of G is, again, with a different action, but again, a rational G module. But now I'm interested in only part of it, okay? So not the whole thing, but some part of it. So set M1 to be the functions in the K algebra that are 0 on the identity. So that's what the 1 stands for. So okay, so set M1 to be the set of f and k of g that are, so that's 1g. I don't know, that's the identity, okay? I'm not going to write that. But anyway, that's the identity of the group. So set M1 to be the ideal of functions that are 0 there, okay? Then that's a G submodule under this action, so that's a G submodule of k of g, okay? And, okay, so G acts on that. It also acts on the square of that ideal, so G acts then on M1, on M1 squared, and on the dual of the quotient. The dual. Okay? And that turns out to be a finite dimensional G module. Okay? Dimension equal to the dimension of the group. Wow, that's great. Okay, so this is a finite dimensional G module. The dimension is equal to the dimension of G. All right.
M1 squared is as an ideal. I mean, you take the M1's an ideal, and M1 squared is the ideal squared.
Yeah, exactly. Yeah. Okay, so I'm going to give this a name. And, I mean, this is not the point of view that I usually take, okay? But it's the most direct route. But we don't have to be direct. But anyway, I'm going to give this a name. So this is a finite dimensional G module, and I'm going to give it a name. I'm going to say the associated representation is the adjoint representation, okay? I mean, I don't really like this point of view, but I'm going to tell you the other point of view, and then you've got two, and you can choose, okay? So let's call this, I mean, not call it, I mean, that is what it's called. So this finite dimensional G module, the associated representation is called the adjoint representation. And that's very important because, well, I'll tell you why. And maybe you've realized it. It's very important because every group has it. That's why it's very important, right? I didn't say, oh, if G is like this, then I'll tell you what this representation is. Like over here, I said if G is GL, I'll tell you some nice representations, right? If G were SP, I would also start telling you the same kind of nice representations, the natural module, the tensor, right? This is any G, and I've got this representation. So it's some kind of very canonical thing, and that's why it's important, okay? All right, so now, further, okay, let's see how much time I have. Okay, so I have a long page here and a half of further remarks about this representation because I really feel that I should tell you the way I like to think about it. Okay, so let's do it. I might then not quite finish what I want to do today, but okay. All right, so some further remarks. About that representation, okay? All right, so, okay, I start by introducing the tangent space. So I have V as, take just V to be an affine variety. I haven't used a V recently, have I? So let's say V is an affine variety. Okay, then for every point in the affine variety, you have the tangent space at that point. So for x in V, then this Tx of V is going to be the space of point derivations on the K-algebra associated. So then let this be the space of point derivations on the associated coordinate ring. Okay. So let's let this be the space of point, well, I'll have to say something as point related to x, point derivations on K of V, i.e., a point derivation, so delta is in there. Well, if it's linear, so delta is a linear map on this coordinate ring, is a linear map, that's a derivation in some sense. So delta of fg is equal to delta of f g evaluated at x plus f of x delta of g. Okay, so in that sense, a point derivation. All right. No, I said that wrong. It's not going from, it's going K of V to K. Yeah, sorry. Okay. This makes sense otherwise. Okay. There's some other derivations that will come back in, and those are derivations on the algebra. Okay. Now, if I set mx, so I have a point in this variety, and if I set mx exactly like I did there, m1, to be the ideal of functions that in the K of V that vanish on x, then it's easy to see then this Tx of V is isomorphic to this thing. Okay? So there's some more geometric interpretation of this thing here. Okay? So this was a very algebraic object, right? I mean, okay, the ideal of functions that vanish on a point, and then you take the square of the ideal as an ideal, and then you take the dual space of that. But this is some kind of geometric object. It's supposed to measure something about the variety in a geometric sense. Okay. I still haven't told you how I like to think about this for the algebraic group, but anyway, that's for any variety. Okay, so now take G to be a linear algebraic group. Again. All right, then now there is a very naturally associated Lie algebra. So all of this is, a linear space, this tangent space, okay? But there is a very naturally associated Lie algebra, okay, in the following way. Then the Lie algebra of G should be the set of the space of left invariant derivations on the K algebra K of G. So left invariant derivations, real derivations this time, on K of G. Okay, so that's a vector space, i.e. a D is in there. If and only if, well, D is a derivation on K of G. And D lambda x is equal to lambda x D for all x. Okay, for all x. All right, okay? So you know if you have linear maps, and then you take the, or if you have a vector space, you take the derivative. Okay, slow down. Okay, I have this guy here. If I take the derivations, that has a natural Lie bracket. Okay, that's the first thing I want to say. So there's a natural Lie bracket on the space of derivations. Okay, and this Lie bracket is actually going to preserve the left invariance as well. So if you have a left invariant derivation and another one, and you take the Lie bracket, that will give you another left invariant derivation. And so this has the structure of a Lie algebra. Okay? All right, so that is Lie algebra. Now, there's a map from, at least a linear map, from this to this tangent space that I defined. You take your derivation. That's just a real derivation on the algebra. And you want a point derivation, so it's pretty obvious what you're going to do. So your derivation knows how to take a function and give you another one, and what you want to end up is in the field. So define theta from the Lie algebra to the tangent space at the identity of G via, okay, theta is going to take a derivation. It's supposed to give me a point derivation, so I apply it to a function, okay? And the derivation knows how to give me a function back, and then I evaluate it at 1. Okay, so there's a way naturally to go from this space of derivations to this space of point derivations, which is the tangent space. Okay, so you show that this theta is an isomorphism of vector spaces. So one shows that theta is a vector space isomorphism. And so I can give this guy a Lie algebra structure. Okay, I mean, otherwise you don't have it. I mean, it's not obvious what the Lie bracket should be here, but it inherits a Lie structure because I can just carry it over from there. Okay, so then this T1 of G inherits a Lie bracket. Okay, all right. Okay, so why do I care? Moreover, if I have a morphism between two groups, well, actually between two varieties, but I'll say it here for groups because that's what we're talking about. So, moreover, if phi were a morphism from between two linear algebraic groups, so phi is a morphism of linear algebraic groups, then it has a differential between the tangent spaces. It's a really natural thing. Then we have d phi, which goes from the tangent space at the, oops, that's bad, but anyway, the identity of G1 to the identity, tangent space at the identity of G2, all right? And this is easy to see what it does, right? I mean, okay, so you say d phi applied to one of my point derivations, right? So now I have to have a point derivation on the right, so then I apply it to a function, okay? And this function should now be a function on G2, right? So this should be delta applied to, but whenever I have a morphism of varieties, I have the morphism on the K algebra that goes the other way, so this is phi star f. Okay? And everything is okay because I'm landing back in the field. You see why you can't do this with the Lie algebra, right? Because here we have functions on the K algebra, right? So somehow this is the appropriate thing to do. And this you do for any variety. I phrased it as if it was for groups, but I mean for any variety. If you have a map between two varieties, then you can get a map on the tangent space. But then, because here the morphism sends 1 to 1, right? If it were general, then you'd have an x here, and you would go over there to phi of x. Okay, so, okay. Okay, so why did I tell you all that? I told you all that because I wanted to say that if you started with a morphism of varieties, a morphism of algebraic groups, and then you took this differential, then, in fact, this differential is a Lie algebra homomorphism. Another miracle. So this has a Lie bracket now, right? Because we inherited it. It has a Lie bracket. And because we started with a morphism of groups here, this thing will be a Lie algebra homomorphism. Okay? So now, better than just getting a map, you get something that preserves the structure that this guy has. Okay. So moreover, if phi is, I think this is the sentences we have, okay, moreover, if phi is this, we have this, and d phi is a Lie algebra homomorphism. Okay. All right. So, in particular, if I give myself x and g, for x and g, I had a map that I liked, right? So I have this Ix, this interior, this map here. Okay, so that was a morphism of, that's a homomorphism of groups for sure. And so I can take its differential, which will go from, well, the tangent space or the Lie algebra, depending on how you want to look at it, but anyway, the tangent space to the tangent space. Okay? Okay, and so that's a Lie algebra. For each x, now I've got a Lie algebra homomorphism, right? Okay, so that in particular, this guy here is a Lie algebra homomorphism. Okay, so I could maybe not write T, but I could write Lie because, you know, I have this isomorphism, right? And the map that I will now define, capital add, which is the map that takes x and sends it to this guy. Okay, so in particular for x and g, we have this. We have that. This is a Lie algebra homomorphism. Okay, and then the map add, which goes from G to the GL, well, of this tangent space, but I want to think of it as a Lie algebra now, so I'm going to write the G. Okay, there's lots of isomorphisms and identifications that have gone on, but anyway, that map there, which just takes add of x to this differential, okay, right, is a rational representation. Okay, the map is a rational representation, and it's the one we had before. So it's not called add for nothing. If you identify everything and do a big exercise, then it's exactly the adjoint representation that I had before. Okay, so remember this guy here as a vector space was isomorphic to the M1 over the M1 squared dual. Okay, and that was where I initially used the word adjoint. Okay, and now I've identified that with this Lie algebra. Or now it is a Lie algebra, say. I've given it a Lie structure. Okay, rational representation, indeed. This is after following through all the identifications that are necessary, the adjoint representation. Okay, now I like this point of view, well, because I'm more comfortable with it. I mean, I'm sure that this M1 over M1 squared dual is fine, but I like this point of view because I'm more comfortable with it. And let me just say, okay. One thing. So let's go back to our example GL, because I mean we should be able to say something, we hope, concrete about one example in this whole picture. So back to G is equal to GLN. Okay. All right. So I wrote here good exercise. Good exercise. Okay, I won't write it on the board. Okay. So the good exercise is I would like for you to know that the Lie algebra of this G is isomorphic to the n by n matrices over K, okay, which I'm now, because I'm thinking of it as Lie algebra, I'm going to call that GLN. Okay, so that's to insist that it has this Lie bracket. Okay, and what would be the map? All right. Well, okay, so I take a matrix here, all right, and then I map it over to, well, I have a choice. It's either a derivation or a point derivation. Let's start with a derivation. So dx, that's a real derivation. So that's in the Lie of G, you know, the left invariant derivations, okay, on the K algebra, all right? And so what would it do? Well, it's supposed to be a derivation on the K algebra, and the K algebra is, you know, K of G is K of Tij, I and j between 1 and n, and y, okay? Because this is supposed to be, GL is supposed to be closed somewhere. It's closed one higher up, okay? So where you quotient out by the determinant of the Tij matrix times y minus 1. So that's your way of ensuring that you get a non-zero determinant, okay? All right? So now I don't want to write this down. I want to think of this as being K of little Tij, where little Tij is the image of big Tij in that quotient. Okay? All right. So what will this derivation do to a little Tij? Dx of little Tij, and that's all I've got to tell you, because after that it's determined, will be the sum TILXLJ over L. So it's like you took this matrix and multiplied it by that one and looked at the ij entry. All right? And then what would the point derivation be? The point derivation, that would be associated to that would be to evaluate that at the identity afterwards, right? So the point derivation would be x ij. Oh, it's beautiful. Okay, so that's a good exercise. Okay, that's nice. All right, so then you can ask, well, what is this adjoint representation? So now I have identified the Lie algebra as just the space, the Lie algebra of n by n matrices, okay? And now I'm supposed to have a way that, and sure enough, notice that it has the same dimension as the dimension of the group. And then I'm supposed to have a way of letting G act on that. And so then you check, and this is the, check that. When you take, for A in G, and X in GLN, that if you take the differential of, the conjugation by A map and act on X, okay, on delta X, okay, right, then that is just delta AX, A inverse. Okay, so this is really doable. I mean, in your spare time. Okay, so it gives you if you identify the Lie algebra with X via this isomorphism over there, then GL is just acting on little GL by conjugation. I mean, it's wonderful. Okay, all right. Okay, so now I'm supposed to stop. So, okay, I'm supposed to stop. I have one page, but I'll start with that tomorrow. So, okay.